In 1687, Isaac Newton published one of the most influential works in the history of science, the Philosophia Naturalis Principia Mathematica. Inside it, he made a claim that would dominate physics for over 2 centuries. Space is absolute, fixed, immutable, an empty stage where everything happens. That idea wasn't just a mathematical convenience, it was the foundation of all Newtonian mechanics. And for 200 years, practically no one challenged it successfully. Until, at the beginning of the 20th century, a clerk at a patent office in Bern, Switzerland, decided to think about what happens when someone travels at the speed of light. His name was Albert Einstein. What Einstein would propose in 1905 wasn't just a correction. It was a complete reformulation of what it means to exist in space and time. But to understand why that was so radical, you first need to understand what Newton actually meant, and why his idea worked so well for so long. For Newton, absolute space existed independently of any object within it. He wrote it explicitly in the Principia. Absolute space, in its own nature, without relation to anything external, remains always similar and immovable. This wasn't a philosophical detail. It was the foundation of his laws of motion. The first law, the principle of inertia, depends on a fixed frame of reference. A body at rest remains at rest relative to what? For Newton, the answer was clear: relative to absolute space itself. His famous bucket thought experiment, described in the Principia, illustrated exactly this point. Newton asked us to imagine a bucket full of water, hanging from a twisted rope. When the rope unwinds and the bucket spins, the water's surface curves upward at the edges. Newton's question was, relative to what is the water rotating? It wasn't relative to the bucket, because at first the bucket spins and the water is still flat. The curvature appears later. For Newton, the water was rotating relative to absolute space itself, and the curvature of the surface was the proof. That argument convinced entire generations of physicists, but not everyone was comfortable with it. In the late 19th century, the physicist and philosopher Ernst Mach published a direct critique of the concept of absolute space in the science of mechanics in 1883. Mach argued that the bucket experiment didn't prove what Newton thought it proved. The curvature of the water, according to Mach, could be explained by rotation relative to the distant matter of the universe, the fixed stars, the galaxies, not by some invisible independent space. For Mach, talking about space without matter made no sense. Space wasn't a thing in itself. It was a relation between things. This critique became known as Mach's principle, and the young Einstein read it carefully. In 1905, Einstein published the paper on the electrodynamics of moving bodies, introducing special relativity. The starting point was simple. The laws of physics must be the same in all inertial reference frames, and the speed of light in a vacuum is constant for all observers. The consequences were devastating for Newton's absolute space. If the speed of light is the same for everyone, then time cannot be absolute. Observers in relative motion measure different time intervals for the same event. This is time dilation. Not speculation, but a direct consequence of the Lorentz transformations, which Einstein reinterpreted with real physical meaning. And if time is relative, space is too. Lengths contract in the direction of motion. Simultaneity vanishes. Two events that are simultaneous for one observer are not simultaneous for another. Newton had treated space and time as separate, absolute entities. Einstein unified them into a single structure, spacetime, where both are relative to the observer's state of motion. But special relativity still wasn't the final blow. In 1915, Einstein published General Relativity, and here the break with Newton became total. In Newtonian mechanics, gravity is a force that acts instantaneously across distance through absolute space. The sun pulls the Earth, and that force propagates through the void immediately. Einstein proposed something radically different. Gravity is not a force. It is a consequence of the curvature of space-time caused by the presence of mass and energy. Einstein's field equation, which he published in November 1915, describes exactly how the distribution of matter and energy determines the geometry of space-time. Space is not a passive stage. It curves, expands, contracts. It participates in physics. This was the exact opposite of what Newton had claimed. One of the first confirmations came in 1919. The British astronomer Arthur Eddington organized 2 expeditions to observe a total solar eclipse, one on the island of Principe off the west coast of Africa, and another in Sobral, Brazil. The goal was to measure whether light from distant stars was deflected as it passed near the Sun, as general relativity predicted. The results, announced in November 1919, confirmed Einstein's prediction. The measured deflection of starlight matched the value calculated by general relativity, roughly 1.75 arcseconds, and was clearly incompatible with the Newtonian prediction. Light curved around the Sun, following the geometry of spacetime warped by the Sun's mass. The results were presented at a joint session of the Royal Society and the Royal Astronomical Society in London. The physicist J.J. Thomson, president of the Royal Society, described Einstein's theory as one of the greatest achievements of human thought. The next day, the Times of London ran a headline declaring that Newton's theory had been overthrown. Einstein became world famous overnight, but it's important to be precise here. Newtonian mechanics was not disproven in the common sense of the word. It continued, and continues, to work extraordinarily well for speeds much slower than the speed of light and weak gravitational fields. What Einstein demonstrated is that Newton's description was an approximation, extremely accurate at human scales, but incomplete under extreme conditions. Newton's absolute space works as a practical model, but it does not describe the fundamental structure of reality. And what about Newton's bucket? Einstein initially believed that his general relativity incorporated Mach's principle, that the inertia of a body would be determined by the distribution of all matter in the universe. But as solutions to the field equations were explored, the picture turned out to be more complex. In 1917, Einstein introduced the cosmological constant precisely to make his equations compatible with a static universe consistent with Mach's ideas. Later, solutions like Gödel's spacetime, found in 1949 by Kurt Gödel, showed that general relativity allowed universes where Mach's principle does not fully apply. In other words, general relativity eliminated Newton's absolute space, but it did not fully adopt Mach's position either. Einstein's spacetime has its own structure, its own dynamic geometry, independent of whether it is filled with matter or not. So, in the end, is space absolute or relative? The answer modern physics offers is more subtle than either original position. Newton's absolute space, fixed, immovable, independent, does not exist. That is a firmly established conclusion of relativity. But Einstein's spacetime is not merely a relation between objects, as Mach proposed. It has its own geometric structure. Curvature can exist without matter. Gravitational waves, ripples in the very fabric of spacetime, were predicted by Einstein in 1916, but many physicists spent decades debating whether they were physically real or merely mathematical artifacts. That debate was settled definitively in September 2015 when the LIGO observatories in Louisiana and Washington state detected gravitational waves produced by two merging black holes over 1 billion light-years away. It was exactly 1 century after general relativity. Those waves travel through empty spacetime. They are properties of space itself. The debate between Newton and Einstein is not just a historical curiosity. It defines how modern physics understands the structure of the universe. GPS, for example, must correct for the effects of relativity, both special and general, to function accurately. Without those corrections, position errors would accumulate by roughly 10 kilometers per day. Modern cosmology, from the Big Bang to the accelerating expansion of the universe, is built entirely on Einstein's field equations. And yet, the deepest question remains open. General relativity and quantum mechanics, the two most well-tested theories in history, are mathematically incompatible at extreme scales, such as the interior of black holes or the instant of the Big Bang. A quantum theory of gravity, whether string theory, loop quantum gravity, or something not yet imagined, will need to redefine once again what space really is. Newton said space was a fixed and eternal stage. Einstein showed that stage curves, stretches, and vibrates. And the next revolution may reveal that what we call space isn't even fundamental, but rather an emergent property of something deeper. The debate that began in 1687 has not ended. And perhaps that is the most fascinating thing about science. The best questions never fully close.